Hello everyone, hi, it's nice to be back today. Last week we discussed a little bit about decimals, fractions, whole numbers and so on. Today we're continuing with our discussion on numbers and we hope to round it up very soon, probably today. We'll be starting with decimals to fraction conversion, and we have a lot to talk about fractions as well. So join me as we hit on this and see what we can achieve. And I hope you followed what we discussed last week, because if you have not, I would advise you go and check it on YouTube, because we've got the recording of last episode, and today's recording will also be on YouTube in case you'd like to catch up on some things I say later on. Okay, so let's see. Here we'll start with decimals to fractions conversion. Decimals to fractions conversion. Now, how do you know what fraction represents a decimal? If you recall, I told you we've got 3 types of decimals and 3 types of fractions. But, the types of decimals are the terminating decimals, the recurring decimals, and what was the last one? The unending one, right? Okay, for example, 22 divided by 7. Well, if you've been given a decimal, what would you have to do to convert that to a fraction? It's just simple. There are only 2 things you can do to a decimal to convert it to a fraction. Just 2 simple things. Either of the 2 of them. Depends on the kind of decimal you've been given. If you've been given a terminating decimal, all you need to do is divide the numbers there by tens. Tens could be hundreds, 1,000, but tens, that's what I mean. And if you're given a recurring decimal, it's going to be divided by 9 or 99 or 999 or 99999, depending on the number of recurring numbers. So let's look at that quickly. We're going to look at it in 2 cases. The first one is the terminating decimals. Okay, and you'll be given, I'll give you just 2 examples. 0.25 and you've got 2.32. Now, second case will be the recurring. I'm very sorry, I'm not writing it properly, I don't know why. Recurring decimals, and I'm going to be looking at 2 examples as well. 0.66666, and it goes on, or it's written as 0.6 dots. That's the way they write it in the exam. So if you see this is what they're talking about. Second case, 0.23 with a dot on both of them. So that means 0.232323. I hope this is visible enough, because it's a pity I have everything muddled up there. So let's quickly look into how to solve this kind of problem. Solution. First case. All right. 0.25 is going to be equal to something over something, and that's all you need to know. So what is the something over something? Can you tell me the numbers you can see here? 2 and 5? If there were no decimal, all you would see is 2, 5, right? 2, 5. If I had 0.205, all I can see will be 205. So you take away the decimal point and tell me what number does that look like to you. Do you get? So, for instance, quickly, if you had something like 2.3202 as the question, and you're told to convert this, and I ask you, what are the numbers you can see ordinarily without considering decimal points? It's just going to be 23202. Fine? Now, so now you can see just 25 as the numbers there. How many decimal places do we have here? 2 decimal places. So because it's 2 decimal places, I'm going to be dividing this 25 by in 1 and 2 zeros. So it's going to be a 100. That's it. If I had something like 0.36, for instance, 0.36, that's going to be 36 divided by 100. If I had 0.367, it's going to be 367 divided by 1000, because 3 decimal places means 3 zeros at the back of a 1. 2 decimal places, 2 zeros at the back of a 1. Now, what do you think about this one? You've got 4 decimal places, so this is going to be 23202, whole number, divided by a 1 with 4 zeros. That's 10,000. Now, this is exactly the same thing with that. And this also tells you that if you have anything like this, a number divided by 10,000, all you need to do is give that number 4 decimal places. If you've got a number divided by 2 zeros, that means 2 decimal places. A number divided by 3 zeros, 3 decimal places. So naturally, if someone had told me to tell the answer for 4 over 100, all I'm going to say is that we've got a 4, and then because of the division of 100, I'm going to give it 2 decimal places. So I'm going to assume we've got so many zeros in front of 4, and I'm just going to count 2 decimal places. 1, 2. So the decimal point is going to be here, 0.04. That's the idea. So it's going to go the other way around, backwards and forwards. It's so straightforward. So when you have that, you're fine. But you're not going to be comfortable leaving it this way, because it can still be simplified further. When you've got a number with a 5 at the back of it, be very sure that 5 can go in it. Any number that ends with a 5 can be divided by 5. Any number that ends with a 0 can be divided by 10. Any number that ends with a 0 can be divided by 10. So what does that tell you? It tells you that this can be divided by 5. And because this can be divided by 10, it can also be divided by 5. How many 5s do you have in 25? You've got 5 5s in 25. So that's so straightforward, I suppose. 5. And how many 5s do you have in 10? 2. With a 0, that's 20. How many 5s do you have in 5? 1. And how many 5s do you have in 20? 4. That's 1 over 4. Now that's the answer to that question. What about the second case? 2.32. Do exactly the same thing. What numbers can I see here if I ignore the decimal point? It's 232. Divided by a 1 with a number of zeros. How many zeros am I going to have there? How many decimal places? 2. So 2 zeros as well. 0, 0. I would love to stop there, but no, I wouldn't do that, because this is an even number and this is an even number. So it tells me that 2 can still go in both of them. So what's 2 in 232? And what's 2 in 100? Well, 2 in 100 is 50. What about 2 in 232? Well, to know that, all you need to do is a rough calculation here. 232 divided by 2. 2 in 2 is 1. How many 2's do you have in 2? 1. How many 2's do you have in 3? 1. There's a remainder. The remainder of 1 comes here. How many 2's do you have in 12? 6. 1, 1, 6. Take note, that is also an even number. So 116 over 50. Because it is an even number, we can still divide further. How many 2's do you have in 50? 25. How many 2's do you have in 116? Again, you can quickly do a rough calculation here. 116 divided by 2. Because it's an even number, we believe 2 can go in it. And let's see. 2 in 2 is 1. 2 in 1 is 0. 2 in 11. Because it's 0, the remainder is 1. So it becomes 2 in 11. 2 in 11 is 5. And what's the remainder? 1. 2 in 16, 8, 58. 58, so 58 over 25. What do you think can go in them? 2 cannot go in both of them because this is an odd number while this is even. 3 cannot go in 25. So what do you think? We can stop there, but just before we stop there, we're going to round this up into a mixed fraction. So this is 58 over 25. But like I told you, it's not good to leave your answer in this improper fraction state. So if we carry on, we're going to have to divide 58 by 25. How many 25s do you have in 58? 1 25 is 25. 2 25 is 50. That seems like we've almost taken everything out of it. So we have 2 25s, and that gives you a 50. You're left with 8 out of 58. You're left with just 8. So the remainder is 8. So you get 2 whole number 8 over 25, and that is your answer. 2 whole number 8 over 25, and it's crystal clear that this cannot be divided any further. Good. Second case of recurring decimals. So let's see how we can convert a recurring decimal. One thing I want you to take home with you is the fact that if it's a terminating decimal, it's written anyhow. It's just written verbatim, okay? There is no crazy dot on top of it. There is nothing funny around it. It ends, it stops. No matter how many decimal places, it stops. For example, it could be 0.253479. Well, it may have 6 decimal places, but it's still a terminating decimal because it stops. A recurring decimal does not stop, and I think we discussed that last week. So I'll just quickly talk to you about how we can convert that to a fraction, which is kind of funny. I mean, something does not come to an end. How do you want to get a fraction out of it? Simple. So let's look at this example. Like I said, we're looking at the recurring decimals to fractions. Okay? Example, well, that's case B anyway. Oh, I think I already gave an example there, didn't I? I already gave an example in the previous question we just looked at. Okay, brilliant. So 0.66666 and 0.232322323. So let's look at the first case, 0.666. 0.6 with a dot on it is going to be equal. Now look at, do you remember the way we did the first case? Now it's almost the same thing, except that instead of a 10, you'll be putting a 9. Okay, so how many decimal places, how many numbers are repeating? Just one number is repeating, and that's 6. So it's going to be 6 divided by how many decimal places? Oh, sorry, not decimal places, but how many numbers are repeating? That's just one number is repeating, so I'm just going to put a 9 there. Okay, so quickly, what if we had 0.8 with a dot? It's going to be, what number is repeating? 8. And how many are they? Just one, so it's going to be a 9. If you had 0.87 with a dot on 8 and 7, it's going to be, what numbers can I see? 87. How many of them are repeating? 2 of them, so it's going to be 99. If you have 0.24 with a dot on 2 and 4 and 5, let's assume it's a 0.245245245. 3 numbers are repeating, and the numbers are 2, 4, and 5. So we're going to divide it with 999, and that's the idea behind it. So the second example will tell us a little bit more about this. So for the sake of the question I gave, I'm only going to attempt this one for you. So ideally, this should be the answer, 6 over 9. But like I said, we should still try to simplify further, because I can see that 3 is a factor. 3 is a common factor, and it's actually the highest common factor. So how many 3's do you have in 6? 2. How many 3's do you have in 9? 3. So the answer is 2 over 3. That's final. I don't think we need to simplify this further. This, we might look into dividing this by 3's, because if you had to divide this by 3, you'd say, how, and why did I say 3? Well, sometimes you need to look for the highest common factor of these things to know whether you can simplify further. And I told you how to discover the highest common factor, right? It's in the previous video, and I believe you can check it. If you still have questions, hit me up. So to find, well, if you divide this by 3, what do you get? How many 3's do you have in 8? 2. That's 6. Remaining 2, right? How many, that comes here. So how many 3's do you have in 27? 9. How many 3's do you have in 9? 3. And in the other 9, 3. So you've got 29 over 33, and that's final. This, I do not think this can go any further than this. So some numbers are just like that. Like you can see 5 is a factor here, but 5 does not anyway divide this. 3 is a factor here, but 3 does not divide that. So where are you going to end? I don't know. I will not give it a... But we could check 7, do you think? But the best thing to do is get the highest common factor, and you know what to do. But if you leave your answer this way, because it is still a proper fraction, you're fine. Unless you're told to simplify further, then you'll know there is something behind that question. So you get the highest common factor first, and you can start simplifying further. So second example in the question I gave was, oh no, where is it? Okay, I cannot find it now, but I think it's 2.32. So number 2, right? 2.32, 2.3 with a dot, 2 with a dot. Now, when you have something like this, how do you convert this to a fraction? 3 and 2 are repeating, so it's going to be 2.323232. But what about this 2? It's not one of the recurring guys, is it? So this is the same thing as 2 plus, so you're going to separate these things, 2 plus 0.32 with a dot on the 2 of them. So what have we done now? We have simply separated the guys that are not repeating from the guys that are repeating. So if you had 24.032 with a dot on just 3 and 2, it's going to be 24. Okay, you can say 0.0 if you want, because this is not repeating, right? Plus, what are the numbers that are repeating? 3 and 2. So it's just going to be 0.032 with a dot on 3 and 2. This is 24 whole number, then 0.032 with a dot on them. If you had this to be a 6, then this can also be a 6. So let's just change this to a 632, and this becomes 24.632 repeating here. And do you know what to do to convert 24.6 to a fraction? All you need to do is divide 246 by how many zeros underneath? 1 0, because you've got 1 decimal place. And do you know how to convert 0.32 dot dot to fraction? Well, the same thing we did in the case of 0.87 dot dot. Divide the number by 2 9s. So you divide 32 by 99. And in this case, you divide 3 2s by 999, because you've got 3 decimal places. Okay? So let's, just a minute. Well, we can confirm that, don't you think? All right, let's do this first case. I'll call it Roman figure 1 now, and this is Roman figure 2. So in the case of Roman figure 1, you've got 2.32 with a dot on the 2 of them, and that gives you 2 plus 0.32 dot dots. I was wrong in that case, but it's just, I'll come back to that. So this is 2 plus 32 over 9. I was wrong with this. Okay, I'll come to that. And that gives you 2 whole number, because that's what this means, right? If you remember in the last video, I told you that when you talk about 2 whole number 1 over 2, it means 2 plus 1 over 2. So here it also means 2 whole number 32 over 99. And it's going to be a little bit challenging to find the highest common factor of this without calculating. So if you're interested to simplify this further, you may need to do the normal prime factor thing, which we discussed last time. So what about this problem? 24.632 with a dot dot appearing on 32, meaning that 32 is the only thing that repeats itself. Now that question is a little bit complicated because I've combined a whole lot of situations right there, but it's nothing we cannot solve, okay? Because it all has to do with what we have learned in the past. So 24.632. I told you the first thing to do is to separate the terminating decimals from the recurring decimal. So this is the same thing as 24.6 plus 0.032 with a cap on 3 and 2. Now this is the same thing as well as 246 divided by 10. Okay, and plus this is the same thing as 0.32 with a dot on them multiplied by 1 over 10. Do you know why? Do you know why we said that? Because there is a decimal. If you're going to if you ever want to reduce the number of decimal places by going backwards, then it means you're trying to divide it. You're trying to multiply by 10. So to cancel that effect, you have to divide it by 10 as well. What I mean is this. And I think can I get a rough paper? Okay. Is it good there? For example, if you have 2.2 and you try to write 22, then that's 22 times 1 over 10, right? That's exactly what we've been doing here. So if you ever want to move backwards with your decimal point, then you are simply implying that you've divided by 10. I mean, something like that. So I believe this is a little bit clear to you. If you're not sure about that, you can hit me up and I'll break this down into details. I'll give you a series of examples. You're not going to forget in a hurry. So this is exactly what we've done. And 246 divided by 10 looks like there are 2 even numbers. So 2 should be able to go in the 2 of them. So 2 in 10 is 5, yeah. 2 in 2 is 1, 2 in 4 is 2, 2 in 6 is 3. So you've got 1, 2, 3 over 5. There is a plus sign here. Okay. Now this is interesting. Something has just come to my attention. We are, by doing this, right, we're making things difficult for ourselves, because this was 24 point this. We could have as well separated 24 from 0.6 so that we don't have to do this kind of big bogus division. So I'm just going to play smart here by repeating this whole thing again this way. 24.632 with a dot on these guys is the same thing, okay, as 24.6 plus 0.032. Okay, sorry about that. And this is also the same thing as 24 plus 0.6 plus 0.32 with a dot on them times 1 over 10, right? Uh-oh, what have I written there? Times 1 over 10. I hope that's visible, otherwise it's going to come out clear in the next line. Anyway, I hate to do this so bad. All right, so this becomes, like I'm going to just rewrite that. 24 plus 0.6 plus 0.32 with a dot on them, multiplied by 1/10. Okay, now so we are happy to do this. 24 plus 6/10, you know we did that previously, and then here you've got 1/10 multiplying something, and what's that thing? 32/99, if you remember, and that is 24 plus 6/10 plus 32/99 times 1/10. And you simplify this into a fraction, you add it to this one, and you add it to 24. If you've got any fraction here, it's going to be 24 whole number, then the fraction. 24 whole number and the fraction. Okay, now that's straightforward, I should presume. Now that's what you get from this. But this is cumbersome. No one is going to giving you something as crazy as this. But you should understand, if you can solve this question on your own, then you'd be very perfect with any of this kind of questions. So I'll just give you this assignment. I'm going to give you this assignment. I'm just going to request one question. 27.632 with a dot on 2 and 4. And I would like you to find the fraction for that. So convert to fraction. Okay, now notice that when we got to this stage, I did not go further. There's a reason I did not go further, and that's because we will be looking at that problem shortly. How do we multiply or add fractions? That's something we'll be looking at very soon. So I hope that's understood. Another thing I would like to talk about before I do that one is converting fractions to decimals. How do we convert fractions to decimals? It's important, we know that, because that's exactly what we might be doing for so long after this. So, and it's actually very simple. We've got two ways of doing it. You've got the long division and you've got the short division. The short division is the one we've been used to. For instance, okay, I'm just going to write fractions to decimals. This is the inverse process. You've got the short division and you've got the long division. But ideally, what we mean by the short division, okay, is when you just cut things out. For instance, 1 divided by 2 is equal to, oh, well, you say, can 2 go in 1? No, 0. Put a 0 behind this and put a dot here. Can 2 go in 10? Yeah, 2 in 10 is 5, so 0.5. Yay, that's my answer. That's the short way of doing it. It's the fastest way if you're in a hurry, but if you need to show your workings, you have to do the long division. Okay, so what is the long division? And it's not really a problem. It's just that it's more detailed. It tells you exactly what you're doing. So for example, we're just going to look at 1 or 2 questions. 56 divided by 4. Okay, now what you do, oh well, that's one question. Next question will be 3 to 4 divided by 8. Okay, so now solution. If you're told to do 56 divided by 4, your answer is going to come up here, but you start writing here 56 and 4. Then you do this. How many 4s can I find in 5? 1. So you write 1. Don't do anything else. That's enough. You've done enough. So what do? 1 times 4 is 4. So you put that 4 directly under the 5 you worked with. And you put a 0 elsewhere. And you subtract to see the remainder. 5 minus 4 is 1. 6 minus 0 is 6. Then you go on. How many 4s do I have in 16? 4. You put your 4 there. 4 times 4 is 16. 1, 6. And you subtract. So what do you get? Zeros. And that's the end. Let's see if the trend repeats itself in the next question. So that was A. B. 324 divided by 8. So this is 324. But let me just say this. The answer is 14. Okay? So divided by 8. How many 2s can go in 3? None. 0. Okay. How many... Did I say 2s? I'm sorry, that was supposed to be 8. How many 8s can go in 3? 0. How many 8s can go in 32? 4. So you write 4 there. You don't do anything else. That's enough. 4 times 8 is 32. 3, 2. Just put a 0 there. And you subtract. 3 minus 3 is 0. 2 minus 2 is 0. 4 minus 0 is 4. Next will be, how many 8s do you have in 4? Okay? Because that's the number we're seeing here. Here we looked at the number as 16. Here we're looking at the number as 4. How many 8s do you have in 4? None. But there's going to be a remainder, isn't there? So you put 0. And then what do? The remainder is 4. So, and that's going to be obvious because 0 times 8 is 0. And that's going to give you 0, 0, and 0. And that remainder gives you a 4. So again, because you have put a 4 again, you're going to put a decimal point there and create a 40. Do you see the line? It's now a 40 because now you have a decimal point. How many 8s can you find in a 40? 5. So you put that 5 there. 5 times 8 is 40. Subtract. That was a subtraction there. Subtract and you get 0, 0. So the answer is 40.5. And that is the decimal conversion of 325 over 8. What if you have like a proper fraction? So let's quickly see that come true. Which is mostly what you're going to be seeing in your past papers anyway. So let's look at a third example. Convert these to fraction to decimals. Sorry, decimals. 2 over. Well, let's say should we say 2 over 3? Let's say 2 over 5. 3 over 7. Now 3 over 7 is going to be recurring, and you see. It's not going to be. It's going to be unending. You'll see that soon. And then C, 9 over 11, also going to be recurring. That's going to be recurring, unending, and terminate. You'll see that. Solution A, 2 over 5. That's going to be a 5, sorry, a 2 here, and the divider is going to be out, the divisor is going to be out. So how many 5s do you have in 2? None, 0. Now 0 times 5 is 0, and when you subtract, you're going to get a 2. Because you have got a 2 again, you're going to put a decimal point there and put a 0 here. Okay? How many 5s do you get in 20? 4. So the answer is 0.4. If you have cause to get the same answer again as the remainder, then you get to put a decimal point and put a 0 there. It's like saying we're not going to repeat the same step again, right? And that's just common sense, I suppose. So we don't want to repeat the same thing. If you've got to get the same answer as your remainder, put a 0 there, put a decimal point, move on. Now 3 over 7, so because it's 3 over 7, 3 is inside, 7 is outside. Now how many 7s do you have in 3? None, 0. There's going to be a 0 times 7 is 0, and you're subtracting, so you get 3 again. Now because you've got 3 again, it tells you that it's time to put a decimal point here and put a 0 behind this guy. How many 7s do you have in 30? 7 times 4 is 28, and I think that's the highest you can get out of it. So 4 places. 4 times 7 is 28, and when you subtract, you get 2. Now because you've put a decimal point there, you're happy to add zeros to the back of any other answer you get. So 0 is added again. How many 7s do you have in 20? 2. 2 times 7 is 14. Subtract, you get a 6. You put a 0 behind it because now we are behind the decimal point, so we're always happy to add zeros now. How many 7s do you have in 60? 8. Because 7 times 8 is 56. And you get 4. How many, if we had got 3 as the remainder or 2 as the remainder, then we know it's going to be a recurring answer. But no, we're getting something different. 4 as the remainder now. How many 7s do you have in 4? Well, because like I said, we can put a 0 there. How many 7s do you have in 40? 5. 5 times 7 is 35, and the remainder is 5, because when you subtract, like I said, it's a new number now. How many 7s do you have in 50? 7. 7 times 7 is 49. Subtract, you get a 1. You're happy to put a 0 there. Do you see? How many 7s do you have in 10? How many 7s do you have in 10? 1. And what's the remainder when you do that? When you subtract, you get 3. And now you put a 0 again. How many 7s do you have in 30? 4. Do you see it's going to repeat itself now? Here. So subtract, you get 28, and it goes on. So you'd notice that we have begun to repeat ourselves here again. So it's recurring. So it's going to have 4 and then 2, 8, 5, 7, 1, and it's going to keep repeating. So the answer, I'm going to write that in red. The answer to this question, therefore, is 0. What's repeating? 4, 2, 8, 5, 7, 1, with a dot on all of them. So that's a recurring decimal. The last one is the 9 over 11, and that's also recurring. You might get to study a trend, okay, in these things. So let's quickly do that, and we can say goodbye to conversions. 9 over 11 to decimal. You've got 9 and you've got 11. How many 11s do you have in 9? None. 0. 0 times 11 is 11. Sorry, 0 times 11 is 0. What was I thinking? 0. So you've got 9 minus 0, you get a 9 again. Because you've got a 9 again, you are happy to put a decimal point there and put a 0 here. How many 11s do you have in 90? 8. 8 times 11 is 88. And when you subtract that, you get 2. Because it's after the decimal, you can put another 0 there. How many 11s do you have in 20? 1. 1 times 11 is 11, and the remainder is 9. Because it's after the decimal, put another 0. Do you see we've come back to this guy? Do you see that? And now 11 and 90 again gives us 8. And 8 times 11 is 88. The remainder is 2. We can put a 0 there. And this is what I'm talking about. We're going to keep, right from here, we're just going to keep repeating ourselves. Recurring. So this answer never stops. 8, 1, 8, 1, 8, 1, and so on. So the answer equals to 0.81 with a dot on 8 and 1. And that is the answer. And you could have known that from the question, because the question was 9 over 11. And when you have 9 over 11, if you had multiplied the numerator by 9 and divided and multiplied the denominator by 9, you're going to have 81 over 99. And 81 over 99 is what we refer to as a recurring decimal of 0.81 with a dot on the two numbers. So that's exactly what to do when you're converting. You need to really study this quickly, properly, because I know I was brief with my explanation, but that's because it's not more difficult than I have been able to solve for you. And it's important that you try that as well. And if you've got questions, we can look at that. So quickly, let's look into addition and subtraction, multiplication and division of fractions. And we're going to be very quick with that because it's actually straightforward. It's almost like the case with whole numbers. And if you recall last week, we spoke about comparing fractions, right, to know which is higher than which one in order of magnitude. And I stated clearly to you that if you need to compare two fractions or more, they have to be on the same platform, on the same level. And that means you have to look for a common denominator. And the easiest way to get a common denominator is to look for the LCM. So in this case, I'm not going to bother discussing into details all the issues of LCM and highest common factors because they were in the previous video. So you may need to do some catching up. Feel free to ask questions if you've got. I don't have a problem with answering questions. If you want private tutorial discussions, I'm happy to give you all that. Okay, nothing is impossible. Take that from me. So quickly, let's get on this. I told you we're going to do additions of fractions, right? Addition. In this case, let's look at 2 over 3 plus 4 over 5 plus 7 over 9. Okay, you want to add this up. So you're going to have to do the same thing, like I said. Make sure they have the same denominator. They have a common denominator. And to have a common denominator, the best thing to do is to find the LCM. So the first question you'd ask is, what is the LCM of 3, 5, and 9? And if you do that properly, you will see that the answer is 45, okay? Now, I will not bother explaining how I got 45 because I've given a long explanation of that already. So therefore, the LCM is 45, and that means to us that 2 over 3 plus 4 over 5 plus 7 over 9 is equal to the LCM of 45 divides everything. Now, how many 3's do you have in 45? Is 15. 15 times 2, okay? Plus, because there's a plus here. How many 5's do you have in 45? 9. 9 times 4 plus. How many 9s do you have in 45? 5. 5 times 7. So that adds up to give you 30 plus 36 plus 35, all divided by 45. And if you do your addition properly, you have 36 plus 35, which is 71, plus 30, which is 101, divided by 45. Now, 101 over 45 is an improper fraction, so you might want to convert that to a proper fraction by asking the question, how many 45s do I have in 101? Well, 45 plus 45 is 90. That's almost everything you can get in 101. So that's going to be 2 whole number. You're left with, when you take 90 out of 101, you're left with 11. So 2 whole number, 11 over 45, and that is your answer. Always leave your answer in mixed fraction or improper fraction. Do not ever leave your answer in an improper fraction, otherwise you're going to get an improper result. And that's not going to be funny. Okay, that's about addition. What about subtraction? So what if I had 2 over 3? So this was question 1, right? Question 2. What if I had 2 over 3 minus 4 over 5 plus 7 over 9? It's almost exactly the same thing. The only thing that changes is the sign. So this gives you an LCM again of 45. So it's important you know how to calculate your LCM, okay? And 15 times 2, like we did in the other case. But instead of plus, it becomes a minus, because this is a minus here. So minus, how many 5s do you have in 45? 9. 9 times 4. Take note of this minus here. And then there's a plus sign here. How many 9s do you have in 45? It's 5. So 5 times the numerator, 7. Now this gives you 30 minus 36 plus 35 divided by 45. According to BODMAS, which is a very important rule you might have already heard about. BODMAS, do you know about BODMAS? BODMAS. Brackets of division, multiplication, addition, and subtraction. It says solve the addition before you solve the subtraction. It goes in that order. So you solve the bracket before you solve the off, and then you solve division problems, then you solve multiplication problems, you solve addition problems, and then you solve subtraction problems. Here you've got 30 plus 35, and you've got minus 36. So let's solve the addition problem so we can do the subtraction once. So this gives you 30 plus 35 minus 36. 30 plus 35 is 65. So you got 65 minus 36. Now, when you take away 36 from 65, which is one of those subtraction problems we looked at last week, 65 minus 36 is basically just going to give you 29. So you've got 29 over 45. So the answer here is 29 over 45, and that is your answer. Okay, I don't think there is anything more to that. Let's quickly look at multiplication now and subsequently division so that we can wrap things up. Is everyone happy so far? You okay? You sure? I'm sure in your mind right now you've got questions to ask. What if this? What if that? Oh, I saw a past question and this was what they said. You know what you should do? Write something on the comment section, or send me an email, or send me a message on Skype, Twitter, and I will make sure I get back to you, okay? I'm always happy to answer questions. I don't mind, really. Okay, multiplication. When we talk about multiplying fractions, it's one of the easiest things to do with fractions. For instance, 2 over 3 times 4 over 5. 9 over 10 times 3 over 5. Now let's look at another one. 24 over 15 times 2 over 3. And the last case, which I would like to look at, 1 over 2 times 11 over 3. Good. Start by solving these ones. Now, one thing you need to know, which is basically all you need to know about multiplying fractions, is that you don't need to look for any LCM. You don't need that. All you need to do is to multiply the numerators together, multiply the denominators together, and that's it. So the new numerator is going to be the product of the two other numerators, and the new denominator will be the product of the two other denominators. So here you go. You've got this straightforward. 2 times 4 over 3 times 5, which is 8 over 15, and that's your answer. But then, is that all there is to it? Yeah, sort of. Again, this is going to be, you can guess what the answer is. 9 multiplied by 3 over 10 multiplied by 5, and that gives you 27 divided by 50. Again, that's how easy it is. But is there more to it? Well, I will say yes, there is something else you need to know. We would be glad to just keep multiplying numerators and multiplying denominators and leaving our answer like that. But because we know that even if we get our answer, we have to look at our answer again and be sure that there is no further simplification. For example, if your answer happens to be 2 over 10, you know that you can still divide, right? So you can still say 2 over 10 is 1 over 5. If your answer is 3 over 33, you know that, well, you should still be able to divide further by going to as low as 1 over 11. So because of this fear of having an answer that is not simplified enough, or because we don't want to have answers with very big figures, we would like to simplify it before multiplying it. So, and in this case, 24 over 15 multiplied by 2 over 3. You will agree with me that 24 and 15 have 3 in common. So we could normally have said 3 in 15 is 5, 3 in 24 is 8. We could have done that before multiplying. That would make life easier for us than multiplying it the way we've been doing the others. And when we get to the answer, we notice that, oh, 3 is a common factor, and it becomes a very big number for us to deal with. Another thing you can do is you can multiply across borders. Like here, you've got 3 here, you've got 24. The 3 here is very happy to deal with this 24 for you if 15 cannot do it. So how many 3's do you have in 3? 1. How many 3's do you have in 24? 8. So you're left with 8 times 2 over 15 times 1, which is 16 over 15, which is one whole number, 1 over 15. One whole number, 1 over 15. And in this case, straightforward again, as we said, 1 times 11 over 2 times 3, which is 11 over 6, which is one whole number, 5 over 6. That is how straightforward it is to do multiplication. Last but not the least, division. Division is exactly the same thing as multiplication, except for the fact that you're going to have to change your division sign to a multiplication sign, and it comes with a particular condition. For instance, 2 over 3 divided by 4 over 5 is the same thing as 2 over 3 times, but look at it, I've said times now. Because of these times I've done here, I'm no longer going to say 4 over 5. Rather, I'm going to say 5 over 4. And the idea is simple. You can easily understand that if I tell you where it came from. For instance, example, 10 divided by 2. Normally you would say that's 10 over 2, right? But do you know where 10 over 2 came from? That came from 10 divided by 2 becoming 10 times, and this 2 became 1 over 2. Because this was 2 over 1, now it's 1 over 2. And that's why we can say this. So even if it's a fraction, it's still going to be the same thing. Turn it around. Okay? Because 4 over 5 is the same thing as 1 over 5 over 4. Okay? Okay? Well, that's exactly what we've done now. I don't want to make things more complex for you, so. Now that we have that, I'll be glad to say 2 times 5 over 3 times 4. Well, let's simplify it further like I advised you to do. How many 2's do you have in 2? 1. How many 2's do you have in 4? 2. That's 5 over 2 times 3, which is 6. Division. Straightforward. It's not more than that. Now, that is division. What if you've got something more cumbersome, like you've got many of them put together, addition, subtraction, multiplication, division? All you need to do is follow the rule of BODMAS, solve the bracket, then the off, and so on. So let's quickly look at what a bracket means. What do I mean by a bracket? So let me quickly break that down for you. A bracket is this sign. That's a bracket. If something is in the bracket, it means that it is representing just one answer. And that answer is what can deal with any other thing outside the bracket. For example, 2 over 3 plus 4 over 5 into bracket minus 1 over 2 plus 1 over 3 into bracket. This means that this one minus that one. Okay? So you're going to solve the bracket. According to BODMAS, you solve the brackets before going to the extent of doing any subtraction. So the bracket here must be simplified first. And this bracket must also be simplified. What's the LCM of 3 and 5? 15. What's the LCM of 2 and 3? 6. When you've got any prime number involved, it shouldn't be too difficult to arrive at the prime factors and the LCM. So this is going to be an LCM of 15 minus an LCM of 6. How many 3's do you have in 15? 5. So 5 times 2 is 10. Plus, because of the plus sign here, how many 5's do you have in 15? 3. 3 times 4 is 12. How many 2's do you have in 6? 3 times 1, 3. Plus, how many 3's do you have in 6? 2. 2 times 1, 2. Still take note of your bracket. 10 plus 12 is 22, so you have 22 over 15 minus 5 over 6. And then you can go on to solve this doing it the way we did the other case. Look for the LCM of 15 and 6 and carry on from there. The LCM of 15 and 6 is 30, and you can carry on from there, but you should be able to find that yourself. Okay, now that's what bracket means. Now bracket could be more interesting if you've got brackets and multiplications outside the bracket and so on. Okay, take note. This is one example. Another way we can use a bracket is if we want to multiply things together. Okay, and for example, 2 into bracket 1 over 2 plus 1 over 3 is the same thing as 2. Like I said, you have to solve the bracket first. 1 over 2 plus 1 over 3 is going to give you 5 over 6, like we did it just now. So 5 over 6. Now, if you have that, what does 2 into bracket 5 over 6 mean? It means that 2 times 5 over 6. So that's what bracket means as well. It also means if there is a number in front of a bracket, it means it's multiplying the content of the bracket. 2 here is 1, 2 and 6 is 3. This becomes 5 over 3, and that is one whole number, 2 over 3. Last but not the least is the off. We're going to look at what off means, because that is another very important thing, and you'll be looking at off more into details when you get to the ratios and percentages. So what do we mean by off? What do we mean by off? 2 over 3 of 6. What's the answer? 1 over 5 of 100. What's the answer? 2 over 11 of 121. What's the answer? That's the question. When they say off also means multiplication. Okay, that's the secret. Off means multiplication. Okay, I cannot write that fully. Sorry about that. So in this question, it's simply asking you to do 2 over 3 times 6. And that is going to be 4. Because 3 here 1, 3 here 2, right? 1 over 5 of 100 is 1 over 5 times 100. And that is 5 here 1, 5 and 10 is 2, and there's a 0 there, that gives you 20. 2 over 11 of 121 is 2 over 11 times 121. 11 here is 1, 11 in 121 is 11, that's 22. What if I say 2 over 3 of 7 over 8? Like I said, it is 2 over 3 times 7 over 8. It's the same multiplication problem, and that gives you, well, 2 can go in 8, right? 2 in 2 is 1, 2 in 8 is 4. That's 7 over 12. I was going to do it the other way around. So 7 over 12. So that is what off means. So now you know what bracket is, you know what off means, and you know division, multiplication, addition, and subtraction. And you're going to obey BODMAS if you follow them in the right order. Now we're done with that one. Let's look at something more interesting. I know I'm running out of time. We're like more than halfway through the 1 hour, into the 1 hour. So we're just going to rush now into surds. What do we mean by surds? I will look at surds and I'll look at powers at the same time because they actually go together in a way. So what's surds, what's power, what's standard form? All talking about the same problem. Let's start by looking at powers, okay? What would you say if I wrote 2 times 2 times 2? You're going to say 8. But if you're not ready to calculate what it is, you can just say 2 raised to the power 3. 2 to the power 3 means that 2 times 2 times 2. What if I said 4 times 4 times 4 times 4 to the power 3? What does that mean? That means 4 times 4 times 4 times 4 times 4 times 4. That's 4 times 4 times 4 times 4 times 4 times 4. And that is 4 to the power. How many 4s do I have? 6. What does that tell you? It tells you that if you have the same number raised to the power any other number multiplying themselves, all you need to do is add up the powers. This was 4 raised to the power 1, 4 raised to the power 1, 4 raised to the power 1, 4 raised to the power 3. It's the same thing as 4 raised to the power 1 plus 1 plus 1 plus 3, 6. Okay? Now, these are the tricks you can always see, and that's all powers is all about. So, if you've got something like a, where a could be any number, okay? A to the power n multiplied by a to the power m, you're simply going to get a to the power n plus m as your answer. Now that's something you can play with. For example, 2 to the power 3 times 2 to the power 5 is 2 to the power 3 plus 5, that's 2 to the power 8. If you've got 4 to the power 2 times 4, it's going to be 4 to the power 2 plus 1, which is 4 to the power 3. Now that's powers for you. Let's take it a step further. Well, this was the first case. Second interesting thing to note, I'm going to look at that in a bit. When you say square roots of 2, when you say cube root of 2, when you say fourth root of 7, what do we mean by that? What do we mean by fourth root, third root, square root? What this simply means, for instance, square root of 2 is simply saying 2 to the power 1 over 2. Cube root of 2 is 2 to the power 1 over 3. So 2 raised to the power 3 is the multiple of 2, right? Like 2 times 2 times 2. While 2 raised to the power 1 over 3 is the cube root. So it's like the reciprocal of the other one. If this is asking to raise something, it's like the inverse function, rather, not the reciprocal, the inverse function. So this is telling you to find the cube root of something. And fourth root of 7 is 7 to the power 1 over 4. So when you see something like that, it's telling you to find the roots of something. Okay? So what does that mean as well? It tells you that if I say 25 to the power 1 over 2, I'm simply asking you to find the square root of 25, and that's 5. So it's not something strange. You should say, oh, well, I think I can do that. But it becomes a little bit more interesting when you have something like this. 8 to the power 1 over 3. Now, we all know the cube root of 8 is 2, right? But how do you think you can show that mathematically? Are you just going to say, well, I know it's 2? No. What you're going to say is that this is equal to 8 to the power 1 over 3. But 8 is equal to 2 times 2 times 2, which is equal to 2 to the power 3. Therefore, 8 to the power 1 over 3 will be equal to, now I'm going to write 8 as 2 to the power 3, and I'm going to put back this 1 over 3 outside, 1 over 3. This is still the same thing as 8 to the power 1 over 3. But now you have 2 to the power 3 to the power 1 over 3. And there is a rule that says that when you've got the power of something that is already a powered number, it's going to be this product of their powers. So 2 to the power 3 times 1 over 3 as the new power, which means 2 to the power 1, which is 2. Now, this will not be a problem for you at this stage, because here are numbers which you can always verify your answers with. But when we get to algebra, you will see that it's good to know how to represent, simplify it further without having to worry about what the answer might really be in the real world. So let's look at the second rule here. The second rule says that a to the power n to the power m is the same thing as a to the power n times m. The third rule, that's what we have just done. The third rule, oh no, that was the third rule. Okay, sorry, I skipped something. I used it, but I did not state it. And that was in this case. Here, the rule generally is that a to the power, the nth roots of an a is still the same as a to the power 1 over n. Now, that is something we have already applied. So, another one is that when you have a to the power n, and you need to multiply that by b to the power same n, you're going to get a multiplied by b, all of them to the power n. So that solves the problem. For instance, e.g., you have 2 to the power 3 times 3 to the power 3. That's the same thing as 2 times 3 all to the power 3, which is 6 to the power 3. And why do you think that's true? Because 2 times 2 times 2 times 3 times 3 times 3 is the same thing as taking this together, taking this together and taking this together. 2 times 3, 6. 2 times 3, 6. 2 times 3, 6. That's 6 to the power 3. So it saves time to understand this rule rather than do all of this out yourself. So these are the common things, okay? You've got the same powers and they are both multiplying themselves. So just multiply them and take the powers out. You've got the same number being raised to several powers. So all you need to do is multiply those powers together and that solves it. But then in the other case, you've got the same kind of number being multiplied with another kind of number, but both of them are to different powers. Keep the same number but add up the powers. Now if you're not sure of this, just play with any number you know, like 2 to the power 3 times 2 to the power 4, and see if you're going to get 2 in 6 places or what. So the last thing under powers that we'll be looking at, and then we can play with some questions, is this one that says a to the power minus n. A to the power minus negative n is the same thing as 1 over a to the power n. Okay, and don't forget 1 is the same thing as 1 to the power anything, so you can as well say 1 over a to the power n. Okay, this negative simply says it's still a to the power n but 1 over it. Find the reciprocal, the inverse of that, the reciprocal of that. For example, let's say 8 to the power minus 2 is going to be the same thing as 1 over 8 squared, which is 1 over 1 over 64. Okay. What if you've got another question like this? 2 over 3 to the power minus 4. That's going to be 1 divided by 2 over 3 to the power 4. And that's the same thing as 1 divided by 2 to the power 4 over 3 to the power 4. And like you should know, when you have 1 over a fraction, it's the same thing as the reciprocal of that fraction. And that's what we did when we looked at the case of dividing fractions, when I said if you're going to convert your division sign to a multiplication, then you have to find the reciprocal of the other one. So that's just the thing. So in this case, 1 over 2 to the power 4 over 3 to the power 4 is the same thing as 3 to the power 4 over 2 to the power 4, right? So that's just the reciprocal of this. You just turn this around and get rid of the negative sign, because you don't need that anymore as long as you've done the reciprocal thing. Also, what if you've got something like this, a to the power n over m? I think this is case 5, this was case 4, right? A to the power n over m. What does that mean? That means a to the power n, okay, and then to the power 1 over m, because this is what we know already. It's like n times 1 over m anyway. Now you're going to find the nth power of a, and then you find the mth roots of all of them. So I mean, that's just what it's talking about, mth roots of a to the power n. So that's exactly what this is. And you need this kind of thing when you're faced with questions, you know, that are questions that require you to play with them. I haven't got examples of such questions here, but they are going to be important when we start looking at past questions. So last on my list of problems to look at about now are the surds. Surds. So what do we mean by surd or surds? Short form is when you have problems in square roots and you don't want to bother looking for the square roots. So there are times someone tells you, it's just like fractions, you know, the way we leave fractions. If I tell you 2 divided by 5, you're like, well, that's 2 divided by 5, 2 over 5. That's because you don't want to go further, right? So if I told you to find the square root of 6, you might look at me and say, well, square root of 6 is root 6. That's short form. Find the square root of 25, that's 5, so we know that. Or if I say find the square root of 50, you might want to leave your answer in the form of 5 root 2, if that makes you happy. That's short form. So in mathematics, you're allowed to leave your answers in short form if you cannot go all the way to look for the square root of any number. So, example, find square root of 50. Number 2, find square root of 48. And number 3, find the square root of 100. Oh no, that's easy. 10. Find the square root of 200. Yeah. So, solution for the first case. Square root of 50. Now, in third form, okay, solve this in third form. What's the square root of 5 of 25? Because 50 is 25 times 2, and we know that 25 has got a square root that we can deal with. So the first thing to do when you have a question like this is to break it into a product of some numbers and make sure that one of those numbers is a square number, like 4, 16, 9, 25, 36, 64, those kind of numbers. So in this case, this breaks down into 25 times 2. And when you have 25 times 2 under a square root sign, it's the same thing as square root of 25 times square root of 2. Because if you remember what we just discussed under powers, you would remember when I said a to the power n times b to the power n is a times b to the power n. Now take note that here you're looking for 25, the root of all of these guys, and that's like to the power 1 over 2, right? So if you had a to the power 1 over 2 times b to the power 1 over 2, it's the same thing as a times b to the power 1 over 2. Now if a is 25 and b is 2, you have 50 to the power 1 over 2, which is the same thing as the square root of 25 times the square root of 2. That's exactly what we did. So we're just obeying the rule here. Now what's the square root of 25? 5. What's the square root of 2? We don't know. So the answer is 5 root 2. 5 root 2 means the 5 times the square root of 2. Okay, and that's the answer to that question. Second question, square root of 48. So what can we break 48 into? What times what? Is there any square number that is a factor in 28? Is a factor of 28? 16? Yeah? You know the best thing to do? Again, look for your prime factors. When you get your prime factors, you can easily look at what number occurs more than once or twice. And if a number occurs twice, then that means that the square of that number is a factor. Tells you a lot, doesn't it? So 48 is 16 times 3. And if you want us to look for the prime factor of 48, I'm happy to do that. But it's going to be 2 times 2 times 2 times 2 times 3. So you can easily say, okay, 16 is a factor. So this goes down to square root of 16 times square root of 3, which is 4 root 3. And then the last case was square root of 200, root 200. That's the same thing. What's the square number you think is big enough here? Because we have so many square numbers inside this one. But you look for the biggest one, which is 100. So 100 times 2. That's square root of 100 times square root of 2, which is 10 root 2. Now that is how to convert or to simplify into surd form. But what then do we want to do with this? What do we want to gain out of this? At times the question is not just to simplify one of them. The question might be to add them together. So how do we add surds? Well, how do we add in surd form? E.g., you've got square root of 50 plus square root of 200. Now, if what we had was square root of 50 times square root of 200, it's the same thing as just multiplying what's under the root sign and putting a big root on them. Just like I told you in the case of powers, a to the power n times b to the power n is the same thing as a times b all to the power n, right? But here we have a plus sign, so you cannot just do that. So you deal with them separately, and if they have the same surd form, then we can add them easily. If they don't have the same surd form, we cannot add them up. So what do I mean? Square root of 50, we have already shown that that is 5 root 2. Square root of 200 is 10 root 2. So this is 5 root 2 plus 10 root 2. They have the same surd form, so we can add them easily. All we're going to do is that because they have the same root 2, then the root 2 is common to them. Then we can go on to add 5 plus 10, and that gives us 15 root 2. This will become clearer when we start looking at algebra, because you will see why it's easy to add 5x plus 10x, really. That's how to add surds, and it doesn't get more complex than that, really. Do I have something to play with? Okay. So that's basically what surds brings to the table. It doesn't get more interesting than that. And just like we did addition, you can have subtraction as well. Okay, you can have multiplication. Let's look at multiplication. Multiplication. Root 48 times root what? 27? Okay, 27. Now, this is the same thing as 16 times 3. And this is the same thing as 9 times 3. So this is root 16 times root 3 times, this is root 9 times root 3. And that gives you 4 root 3 times 3 root 3. Now, because you're multiplying them, you don't care if they have the same surd form or not. This is in the same surd form, so fine, I'm happy to just do the same thing I will do even if they were not in surd form. And what's that thing? This is 4 times root 3 times 3 times root 3. Like, you know, 3 root 3 is 3 times root 3. 4 times 3 is 12. Root 3 times root 3 is 3. So you've got 4 times 3 times root 3 times root 3, which gives you 12 times 3. And that gives you 36 as your answer. Okay? So like I said, even if they were not in the same surd form, it will be as easy as it just was here. Second example, 2 root 3 times 4 root 5. That's going to be 2 times root 3 times 4 times root 5. That's 2 times 4 times root 3 times root 5. When you have root 3 times root 5, or root a number times root another number, don't be afraid. All you need to do is multiply the two numbers together and retain the root on top of them. It reminds me again of this surd form problem where we said if you have not this one, sorry, not this one, but then it all adds up to the same thing. You see here it says a to the power n times b to the power n is a times b all to the power n. In this case, you've got 3 to the power half times 5 to the power half, which is going to be 3 times 5 all to the power half. So that's going to be 2 times 4, 8 times 3 times 5 all to the power half. And that gives you 8 root 15. That's the answer to that question. Happy now? So basically, that's all swords has got to offer. It doesn't get more tedious than that. And if you see anything more tedious, call my attention to it, okay? So the last thing to discuss here, well, there are just two more things to discuss. Standard forms, okay? Now, I have a feeling that we should do that really quickly, because once we do this, we can move on to very interesting aspects of the syllabus like algebra, which everyone is eager to get to. So, standard forms. And there is pretty nothing much to say under standard forms, other than the fact that standard form is just a way of writing numbers, big numbers, in power forms, right? For example, if I had told you that 2 is equal to 2 raised to the power 1, I mean, will you be surprised? No. If I had told you that 4 is equal to 2 raised to the power 2, I mean, are you surprised? No. But this is not what we mean by standard form, right? This is what we mean by indices. You're trying to show us the roots, the powers it could get to. But what if I said that 10 is equal to 10 to the power 1? Will you be surprised? No. 100 is 10 to the power 2. Would you be surprised? No. What if I said 10,000 is 10 to the power 4? Because there are 4 zeros. Would you be surprised? No. All right. 0.1. What will that be? Is it 10 to the power minus 1? Why is it 10 to the power minus 1? Why? Because this is the same thing as 1 over 10. And 1 over 10, like I explained to you in the case of powers, is 10 to the power minus 1. 0.01 is 1 over 100. And that's going to be 1 over 10 squared, right? And that's going to be 10 to the power minus 2. So 0.000001. That's going to be, how many zeros do you have? How many decimal places? 1, 2, 3, 4, 5, 6. That's 10 to the power minus 6. This had 1 decimal place, was to the power 1 minus 1. This had 2 decimal places, was to the power minus 2. This has 6 decimal places, is 10 to the power minus 6. When you had just 4 zeros, it was to the power 4. When you had 2 zeros, it was to the power 2. When you have 1 zero, it's to the power 1. Is it making sense at all? So that's just all you need to look at, right? You don't need to worry about how this became this, and this became this, and this became that. You're making your life easier by just knowing the ways to calculate them. Count number of decimal places and give it a minus sign. Count number of zeros and give it a plus sign. Okay. So, now that's standard form, right? But how do we make use of this? We make use of this when we want to make life easy for ourselves. For example, convert to standard forms. 0.025, 0.367, 2.12, should we say 2? Let's say 32.12, because that was almost in standard form already. Solution to this. Okay, when you talk of standard form, we want to see something times 10 raised to the power something. Okay, we want to see something times 10 raised to the power something. That's all we want to see. So in the case of 0.025, what are we going to have multiplied by 10 raised to the power something? Now, this is all you need to do. Look at the whole of this. Look at all these numbers. What are the numbers? What are the real numbers you can see? 2 and 5, right? Natural numbers, 2 and 5. Now, let's assume you've got 2.5. So we're going to put a decimal point here now. So it's 2.5. Okay? Now, the idea is that we want to have just one number out, one whole number, and we want the rest to be decimal places. We want this one to be 3.67, and we want the rest to be decimal places. We want this one to be 3.212, and we want the rest to be decimal places. So that's what we mean by standard form. Number 4, if you had 3247, we want it to be in the form of 3.247. That's what we mean by standard form. Okay, everyone wants life to be easy. So now what do you do? 10 to the power what? 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 Just count the number of steps you've moved to decimal. That's all. If you've moved your decimal backwards, then it's going to have a negative power for 10. If you've moved the decimal place forward, then you're going to have 10 to the power positive of that number of places you've moved it to. We had our decimal point here before, and we moved to 2 point something. How many places have we moved backwards? 1, 2. That's 10 to the power minus 2. Here we've got 0.367, but we've moved it to 3.67. How many places have we moved backwards? 1 minus 1. How many places have we moved? Forward or backwards? Forward. How many places? 1. We moved this way, right? So it is power 1. And what about this one? The decimal point was here. We moved 1, 2, 3. So how many positive? But what? 3. And that's the answer. Now that is all about converting to standard form. That's just what it's about. Know what numbers you've got, know how you want it to be written. We want just a whole number and the rest should be decimal places. Now that we know that, how many places have we moved our decimals? Have we moved the decimal point by 3 places or 4 places? If it is, fine. Is it forward or backwards? Backwards, negative. Forward, positive. Happy? All right. Finally, this is important for a reason, and you will see that shortly. And it's about unit conversion. Unit conversion. Now, why do we bother ourselves really about standard forms? It's about unit conversion. Everyone wants just one number, really. No one wants to hear 1,544 million. No. No one wants to hear 262.79. No. Just give me one number and let the others be decimals, so that if I want to approximate, I will know what to do. For instance, example, convert meters to kilometers. Why do you think we like to convert units from one to the other? Like I just said, everyone wants a simple number. Instead of saying 1,000, we want to hear 1. So the other zeros should be a unit. There should be a unit for that. And that unit is kilo. So 1,000 meters is 1 kilometer, where kilo represents 10 to the power 3. So 1,000, right? 1,000 is the same thing as 1 times 10 to the power 3, according to what we just looked at, standard form. Now, if this is regarded as meters, then this will be regarded as kilo. So if we say 1,000 meters, we want to actually have it as 1 kilometers. So this represents 10 to the power 3. So if you have 1,250 meters, that's the same thing as 1.25. Then you ask yourself, how many zeros do I have there? How many tens do I have? Well, you've moved the decimal point from this place 1, 2, 3. So that should have been times 10 raised to power 3, but we're just going to call it kilometers. And that's how we convert units. And that way we can have several units, several types of units really. But the common units we all play with is money, isn't it? Pounds to pence, dollars to cents. Okay. Now that's what we mean by conversion. We can even convert other things as well, you know, weights, you know. So let's look at that. Second example. Convert pence to pounds given that 100 pence is equal to 1 pound. Okay, 100 pence is equal to 1 pound. So how do we convert that? So the first case, 80p. Second case, 990p. Okay. Now, how do we convert this to given that 80p is not even up to 100 pence, so it's not going to be up to 1 pound. So the question is, how many pence? How many pounds? Well, the question is, how do we do that, right? So basically, this is a very funny question, really. What you need to do is to find how many pounds you've got, or how many 100 pence you've got in 80p. So that's basically the first question. 80p is the same thing as 80 divided by 100, and that converts it to pounds, and that is 0.8 pounds. Okay, basic conversion. For example, in this other case where you've got 1,250 meters, where you already know that 1,000 meters is 1 kilometer, to convert that you need to just divide this by 1,000 meters, and that gives you this in kilometers. Okay, apparently this could have been treated in the same way as standard form, but then you will have to do something else a little bit different by having 0.8 first. Okay, so the second part of the question, 990p to pounds, is going to be 990 divided by 100 pence, and that will give it to you in pounds. And if you divide this by 100, if you remember how what we did about converting fractions to decimals, if you've got 2 zeros, then you're going to have 2 decimal places. So that's going to be 9.9, right, pounds. And that's your answer. I'm so sorry that I have not taken my time to break this into so many examples, but this is basically what you can expect in any question like that. If you come across any problems in this, hit me up and I'll be happy to slow down a bit for you. Now, the last thing to discuss here, which is going to be very quick and brief, is estimates. What do we mean by estimates? Okay, what do we mean when we estimate things? Estimate means that you are not going to be worried really about about calculating the actual answer, but you want to have an idea of what it could be. For example, if I say 9 over 10 of 20, 9 over 10 of 20 is almost the whole 10 over 10 of 20. So 9 over 10 of 20 is almost 20. That's an estimate. Okay, so, but in some very complex equations, you're not going to be bothered about calculating the actual answer. So what you do is you round things up to 1 or 2 significant figures, yeah, and you solve them. For example, 2.023 times 11.1 all over 3.13